Morning, all. So that's quite the act to follow. I'm going to do my best here. So I'm a professor here at UMBC, and my research is on the intersection of robotics and language, so natural language. I don't seem to have a clicker. Okay, got it. Okay, so how can we use robots usefully in human environments, right? And what do we expect from physical computers? Right now, the robots that we have look a lot like this image on the left. They're big, they're complex, they're expensive, and they do one thing and one thing well. They do only one thing well, right? Whereas what we want to see in our robotics is something like this image on the right, where we've got robots that are in human spaces, interacting with people, doing the kinds of tasks that people want them able to do. And this raises some higher level questions that people working in the human-robot interaction space need to ask. Like, what is a human environment? What is a human-centric task? Where do we want to start seeing robots? And when we go and put together the robots and the humans in the human environment, what kinds of interactions do we want to see happening? How do we want humans and robots to work together, to collaborate? And the core of this talk is I'm going to talk about how we can use verbal interaction, how we can generate and perceive speech. What do we want to say to robots? What do we want robots to say to us? How and when do we want them to say that? And that's a hard problem with a lot of complex sub-questions, like how do robots understand the environment and the context around them, the space in which these speech interactions are occurring. So in this talk, I'm going to talk about building robots that use grounded language to actually give humans the kind of interaction style that we want, that can go in human-centric spaces and be useful for novel capabilities, that we can do things like take a robot and plonk it down in a human kitchen and have it actually be useful in a non-repetitive, non-purely mechanical sense, right? And as you'd imagine, this is a really multidisciplinary problem. It needs robots, obviously. It needs natural language, the interactions between robots and the kinds of language that humans use comfortably by themselves. It needs HRI, human-robot interaction. How can robots and humans interact with one another in a way that people find comfortable and natural and engaging and useful? And it requires machine learning, because there's a tremendous amount of stuff in the world. We can't preconceive, as programmers, we can't preconceive of everything anybody might want a robot to do. So we need robots that go out into these environments and learn from people how to engage in the interactions that they need to engage in. And here I'm going to talk a lot about robots and humans collaborating. That is, all of the technology I'm going to talk about is about how can robots do things with people rather than caged off in these kind of safety settings where they have dedicated workspaces. And here, I consider natural language, I consider communication with robots to be successful if a robot does what a human intends for a robot to do. That is, if the robot is successfully collaborating with the person, then I consider it to understand what's going on. I consider language to be understood, even if it's not necessarily how we would use understanding of language in a colloquial sense. And one of the key aspects that I hope you'll take away from this talk is that robotics and natural language, which are two very data-heavy fields, really need each other. Robots need language in order to interact gracefully with people, but language needs robotics to provide context, to provide information about the world. So just you know, if we've got a set of symbols and we're trying to understand them, we're trying to understand what this guy is saying to the systems in his environment, just pop quiz. What's he saying? Push up, shut up, go up? We have no idea, right? It's impossible to understand language given what we have so far. But when we're talking about robots, we've got physical context. We've got the sensor information that robots are providing in the setting. And once you've got that, it becomes much clearer what's going on and what a person wants a robot to do. That's why language needs robotics, is to understand this kind of grounded language. And what makes language grounded is the idea that it doesn't exist in a vacuum. Language means something in a physical world, in the physical context in which it occurs. Language symbols have to be connected to some kind of physical referent. And this is, you know, this is sort of intuitive, right? If we want to understand what an apple is, we don't lock ourselves in a closet with a stack of dictionaries and read as much text as we can about apples, even though that's how natural language understanding pretty much works. If we want to understand what an apple is, we pick it up, we rotate it around in front of our sensors, we smell it, we look at it, we interact with it. And that means the language is grounded out in this physical context that the robot can provide. And just to define the task a little more clearly, the core idea here is that what we're doing is we're taking natural language and a physical setting, physical percepts being perceived by the robot, by the different robot sensors, and we're bringing them together to try to disambiguate what the meaning of the language may be, given that it's co-occurring with this sensory data. And just to go technical for a minute, the idea is that we're building a language model of some kind. Conceptually, we're trying to learn a language model that takes the natural language that people are using and parses it into something that is computer understandable, implicit or explicit, but understandable by the underlying system rather than by the people who are using that language. And at the same time, we're trying to build a world model of something that looks at the world and divides the space up into things that have sort of different perceptual characteristics. And then we can take those and combine them to say, okay, I understand things as queries against the world. If somebody says, hand me these blue objects, I can say that we're talking about the set of objects that has, you know, this perceptual data with this associated language. And that way, all of these components of the actual function that is the core of the machine learning that we're doing are elements that are part of the robot's interaction with the world and the robot's interaction with language. So I'd like to give you a demonstration of what that kind of sort of learned system should behave like. And I hope the sound on this works, we'll see. Okay, it looks like the sound is not working. So the robot says, I'm ready. And the grad student says, okay, could you pick up the pepper and the green arch thing and this toy right here, please? And the thing that I'd like you to take away from this is that none of the robot's actions here are anything that were programmed in. This is entirely a learned interaction where the robot has interacted with the person.
Arch thing and this toy right here.
Okay. The people have sat down, talked to the robot about objects, described different things, described them using whatever language came to mind for them, and the robot has used that to build a model of what's going on in the world. So the pepper and the green arch thing and this toy right here with a gesture is three sort of different complex kinds of learning that the robot has learned from those interactions with people. And this is going backwards now, okay? So one of the things to note here is that language grounding, the kind of language grounding that I'm describing, is a multifaceted problem. No one thing is going to be the silver bullet. So right now, there's a lot going on in the deep learning space. There's a lot going on in information theoretic spaces. But I'm not going to talk about the solution. There's no single silver bullet that is, and this is how robots learn from language, because it's a big, complex space with a lot going on. And one way to think about grounded language is it's a sort of a shared embedding problem. The idea being that you've got objects that exist in the real world, like, say, a mug, and we've got different ways of referring to that object, none of which are the object itself, none of which are the Platonic ideal object. The object is intermediated to us by the language that we use to describe it, and the sensors that we use to perceive it, the eyes that we use to see it, and what our brain is doing, parsing that interaction. And that's a useful way of conceiving of the problem because we've got a lot of mathematical mechanisms for understanding how to learn that kind of shared embedding. How can we take this sort of real thing that in one projection is described by language, in another projection is perceived by vision, in a third perception is perceived by depth, and so on, and use that to learn a model. So that means you can learn alignments between heterogeneous data sources, where you're learning a projection of data to some embedding. And you can use all kinds of different machine learning methods to learn from that overlap, the semantics of the paired data, to learn the interactions between the perception and the world. And we want to use data from these different domains, from the sensor data that we've got and from the language that we're using as labels for that sensor data. So the core idea is that we want to take the physical objects, the physical perceptions, and the language perceptions and force them to be close together, force them to be in the same part of this global embedding space, this shared space, while we take things that are separate, things that are negative examples, and force them to be further away. So we want to take this high-dimensional space and say the language and the perception of the same thing should be physically close together. And we do that by defining vision, what can we see, perception, as an anchor point. Okay, this is the physical anchor for the space. And the language, here it says a red tomato on a plate, and we say we want to force that anchor point and that positive point to be close together, while we force this negative, the pink gorilla eating the bird, to be separate. Now, our data set doesn't have any pink gorillas in it, so this does a pretty good job foreshadowing some of the difficulties that you encounter when you're trying to deal with language, is that people say some of the weirdest things. People just, I have no idea where some of the stuff in our data set came from, but it made sense presumably to the person who was describing it to the robot at the time, right? And once you've done that, once you've forced those embeddings to be close together or far apart, then hopefully you can take something new. You can take somebody saying something like, hand me the tomato from the plate, and you can say, okay, I've got the physical, I've got all of this perceptual data, and I know what is closest of the things I perceive. I know what's closest to the language I'm hearing. I know what you want me to do. Right. And that works really well. You can see that you've got this sort of, this vision, a map of the vision and a map of the language, and it's color-coded by the different object classes, like water bottles and pears and staplers and syringes. Our data set has a lot of medical supplies and a lot of office supplies and a lot of kitchen supplies. And you can see that those things are close together. And what that means functionally is that What that means functionally is that if you go to this system and you say, all right, hand me the blood pressure cuff, it can look at all the objects in the environment and say, okay, I understand which of these things must be the thing that you're referring to. I can do what you want done. And so far, I've been talking about some specific methods because I want you to understand the kind of the machine learning efforts that underpin the work that we're doing. But in fact, when people interact with one another, when they interact using language, it's a very multimodal kind of interaction. People use speech, they use gesture, they use vision, they use, gaze. When we interact with one another, we use a lot of different mechanisms beyond just the contents of the words that are being spoken. And real language, when you get into real language, when you get into, in particular, I want to talk about speech, you start to see that speech doesn't have a lot in common with the kind of text that a lot of natural language processing operates over. So if you ask somebody to type descriptions of objects, they say things like, it's a black and yellow flashlight, right? Easy, clean, easy to deal with. But if you ask them to describe something in speech, you get a lot of, okay, now I'm going to describe two objects. They have the same shape, but they're a few degrees rotated around. The language tends to be agrammatical. When we speak, we make a lot of small grammatical errors that we don't hear, our listener doesn't hear, our brains just skim right over and correct them for us. There's a lot of disfluencies, places where you pause, go back, say Spoken language is not that similar to typed language, but when we're talking about using language with robots, we're really envisioning speech. Right? We're really not envisioning following our robot around with a keyboard strapped to it or strapped to us. We're really envisioning walking to the robot and saying, okay, dice the onion for me. Hand me the blood pressure cuff and then the syringe. And automatic speech recognition is not in any way the solution for this, for a couple of reasons, of which the most critical is automatic speech recognition doesn't work that well. So how many people have something like an Echo or a Google Home or talk to their phone, use Siri? The speech recognition, how many people's speech recognition works perfectly every time? Right, I think I saw a hand, but I'm hoping it was sarcastic. Speech recognition doesn't work perfectly. And it, in particular, and one of the things that I'd like you to bear in mind for a little later in this talk, is it doesn't work consistently across different groups. Automatic speech recognition doesn't work as well for female voices. It doesn't work as well for voices that aren't unaccented American English. So not only does it not work that well to start with, it has a sort of an inequitable differential performance across different groups. So we want our robot to learn from speech. We want our robot to learn from a combination of speech and sensing data that's coming in. And one of the problems that you encounter when you're trying to do this kind of learning is this data set doesn't exist. There is no data set that's just a bunch of complex robot sensor data combined with natural spoken language of people at a microphone. So we had to set out to collect this data set, and this involved collecting 16,000 spoken descriptions of objects in the three categories that I described, as well as typed descriptions so that we could use them to compare how well are we doing with speech as opposed to typed text, and how well are we doing with speech as compared to automatic speech recognition text. And if you take the speech data that I'm describing and feed it into the machine learning system that I described previously, what you find is that using speech outperforms using automatically transcribed speech, something that's gone through ASR, outperforms it immediately. We didn't have to do any work to make the system operate better. Pretty much as soon as you featureize speech and use it as an input directly without at any point going through a text intermediary, the system is learning from a combination of speech and perceptual inputs of the environment, what it's seeing, what it's perceiving, what it's sensing, without at any point this going through any kind of written English that a person could view. And it immediately outperforms other systems, which makes a lot of sense, because automatic speech recognition is lossy, right? It's what happens when you take speech and drop a bunch of the information out of it. But it was still nice to demonstrate that we can have robots that are learning how to do these tasks, learning to accomplish what people are asking them to do, just based on this sort of speech-based interaction, without going through any of the kind of traditional text phase that a lot of this work relies on. Now, I was talking about how we care a lot about the differential speech, how some people are better understood by ASR than others, some people are, as a result, better understood by robots than others. And in order to understand that, we went through this 16,000 speech data set, which was provided by about 550 speakers, and we annotated their sound files with characteristics. So, you know, my poor grad students went through all of this data and annotated these sound files as to characteristics about the speech itself. Does the speech sound like it's coming from a male speaker or a female speaker? Is it accented speech? Is the voice creaky or hoarse in a way that is associated with age? Because another thing that ASR systems don't do very well is cope with people outside a fairly narrow age range, as well as things like, you know, how are we affected by the background noise? How are we affected by the volume of the language that was collected? And what we found is that the transcribed data does do worse across different groups. The transcribed data doesn't do as well for female voices. The transcribed data doesn't do as well for, in particular, this was the most notable effect, accented speech. But the speech-based system evened out those differences. So if you're learning directly from speech, if you're taking somebody and putting a robot in their kitchen and saying, okay, the robot is going to learn how to refer to things from you, from the speech that you are giving it, then when you come back and say, okay, now I want to use that robot, now I'm going to use that speech to describe what I want it to do, to describe the things around it that I want it to interact with, it does better, right? It does better when it's learned directly from the individual groups that are going to be talking to it, which makes a lot of sense. You would expect a system to perform better if it's learning from the people with whom it's going to be operating, but that's not how we normally do machine learning. We normally do machine learning by taking these very large data sets and then saying, this will sort of work for everybody, and it'll work better for some groups than others. Whereas if you actually take something that's learning directly from speech, from the interactions with people, and go directly to interacting with those people, it's going to outperform things that are trained on these very large generic data sets. So what we've learned is that using speech to interact directly with robot machine learning systems results in systems that are more equitable as well as more effective. There's not a trade-off between accuracy and effectiveness for different groups. So I've been discussing mechanisms for grounded language learning that are very flexible. We can swap in different learning mechanisms, we can swap in different data sets, we can swap in speech for text, which is a fairly major change, right? And even sort of different, we can even swap in things like gesture, you know, pointing at an object and saying, pick up that one. But anytime you have a learning system, that is that flexible, it's going to be extremely data hungry. And this is an extremely data hungry problem. And human-robot interaction is a field that has data problems anyway. To do good human-robot interaction, you can't just run millions of simulations. You have to have people, you have to have robots, you have to have them interacting in real time, in a real setting. And if you want to have them in a variety of settings, if, for example, you want to be like, okay, now we want to test having this robot doing this kind of learning, engaging with people using speech in a hospital, or a picnic table, or, pick your setting, then it's not easy to just drag robots out to whatever the setting is. And that's particularly true right now when even human-human interaction is somewhat constrained, right? So, broadly speaking, one of the problems that we encounter when we're dealing with this is, where do we get the data? And one of the answers that the field of robotics is exploring is called sim to real, simulation to reality. And the last talk touched on this. How can we use virtual reality settings to learn the things that we need to know in the robotic space? How can we take information provided by people in a simulation, learn from it, and have the people also learn from it, have the people do their interactions, and then bring it into the real physical space in which robots exist and operate? Broadly speaking here, the goal is to build a simulation environment where humans and robots can engage in robotically realistic interactions. And a lot of the time in HRI, the goal in sim to real stuff in simulation is to have people learn things. That is, people can use simulated environments to learn to control a robot. Or we can ask questions like, how comfortable is a person with a self-driving car in simulation? When does the person get uncomfortable? And that's all useful from a human side, but I'm talking about learning from the robot side. So the idea here is, how can we create a setting that is realistic enough from a sensory perspective that the robot can learn from a person in virtual reality engaging in the kind of teaching interactions and speech interactions that I've been describing. And how we accomplish this is we have a variety of virtual reality settings. We've got a physical cave, which is just a big curved wall of monitors where you stand in it, and it's very similar to being in a physical setting. But we can also use off-the-shelf virtual reality hardware, like a gaming-style headset. And interactions can take place in that setting where participants sit in that virtual reality setting, describe things to a robot, teach the robot about the tasks that they want the robot to do. The robot perceives a simulated version of what it would be perceiving if it was in the real world, learns the model that I was describing, learns a model of language, learns a model of perceptual interpretation. And then we take the robot and the person into the real world environment, and we say, okay, can you accomplish the task, right? And that work is ongoing. Right now, we're doing a lot of work on language grounding over raw speech, where in the training phase, people come into this virtual reality setting and describe to the robot a bunch of objects in a kitchen and describe a lunch packing task. How can you pack a lunch? The robot can learn from the things that are being described. It can also ask follow-up questions like, is this also a, or can you tell me more about the, and get to the point where the robot understands the human instructions enough that it can accomplish a task. Then the robot identifies the described items, and we're in the process of moving this into a physical robot in a physical lab to demonstrate that it can do the task, that it can actually do things like pack a lunch for somebody based on all the learning that it's had in the virtual reality setting. And one of the things that we have, and I'm also leaving a lot of time at the end, but hopefully I'm leaving it for questions. Unfortunately, I don't have a life-changing story to relate. Fortunately, I don't have a life-changing story to relate. But One of the things about this environment is about this doing things in virtual reality is that we've got the capability of building sort of arbitrary environments relatively quickly. So I don't know how many of you are familiar with UMBC, but here on the right, we've got a picture of our primary dining hall. This is the True Grits dining hall. And on the left, we've got the scenario in which the robot is operating to do the learning and performance task. So you can see that it's relatively detailed. There are a lot of individual food objects that the robot can pick up. If you tell it, get me a slice of pizza, it can interact with the environment, pick up the individual objects, and so on. And all of that got put together without us necessarily needing to haul a robot over to the dining hall, get permission to have people come in and do the experimental training in that setting and so on. Here's another setting. This is our hospital scenario, and this only took us a couple of days to set up. And you can see on the bottom, you can see the robot's sensor data. Here's what the robot sees using visual and depth data. And at the top is what the human sees. It's just the robot moving around in this hospital setting. And this setting really only took a couple of days to set up. And if you've ever done any experiments with robots, you know that you don't set up novel experimental setups in a couple of days. So the idea is that we can use this virtual setting to tie back around to this language understanding and speech understanding with the long-term goal of having the robot able to learn quickly in a variety of environments. And it's worth noting that not every research group, not every interested party has hundreds of thousands of dollars to spend on robots. So demonstrating that it's possible to do real meaningful HRI research in simulation in this way also has the potential to expand the accessibility of robotics research to anybody who can afford, a server and a VR headset, a few $100s rather than a few $100,000. So broadly, learning grounded language is a complex space that has a lot of associated tasks and problems. This is the sort of 10,000-foot overview. I've tried to give you a flavor of some of the key problems that people working in this space are addressing, some of the work that's going on in my group. But the takeaways are that it is a complex space that requires a lot of distinct tools and perspectives and learning approaches. And learning directly from a variety of perceptual kinds of interactions and from a variety of people is key. Hopefully doing some of this learning and simulation will extend the reach of what we are capable of addressing with our robots and the settings that we're capable of putting them in, taking them out of factories and putting them in human-centric environments and human spaces where humans can explain what the robot should be doing. And of course, this isn't all work I've done myself. I've done this with a number of amazing collaborators, and in particular with a number of amazing grad students who do all the actual work while I give the presentations. So with that, we've got about 10 minutes left, and I hope there are some questions. Thank you very much for your time.
I do have a question. So I'm curious if any of your work has looked at the use of emphasis and particularly sarcasm. So if someone says, Cynthia's really helpful versus Cynthia's really helpful, right? Those have opposite meanings. And even things like there is a white coffee cup versus there is a white coffee cup. Those have two very different meanings. Has your work looked at that at all, or do you have any plans to look at that at all? And what sort of results have you seen, if you've seen any?
Right. So we're not looking explicitly at prosody, at how people say things. That's not something that is built into what we're trying to accomplish. But it is, because we are learning directly from speech, it is something that you could imagine picking up, like if, for the very task-oriented stuff we're doing, I want you to dice an onion and put it in the pot. For example, there's not a lot of different interpretations of the different prosodic ways that people can say things, but if people were to use language that is emphasized very differently to mean different things, to refer to different things, then the way that we are featurizing language and learning directly from the speech should be able to pick it up. So it's sort of encapsulated in the speech understanding. That doesn't necessarily mean that we would immediately learn from it and handle it well, but it's not inconsistent with the technology that we're using. It's a great question.
You can't dice an onion sarcastically?
I can, but I can do anything sarcastically.
So a couple things, should be quick. When you were describing the non-transcribed just speech to perception, so you're literally taking audio files and feeding it into a machine learning system?
That's right.
Okay.
We're going through featurization. There's a number of different ways to featurize audio, so that you're picking out things like high and low points for pitch and things. So it's not a wave file going into the machine learning system. It's a featurized wave file.
Okay. Are there any Fourier transforms going on in?
There are, yeah.
Okay. That seemed like that sort of thing.
Yeah.
Odd question maybe, but I've kind of seen conversations between two people with different accents, each of which doesn't think they have an accent and that the other one does.
Right.
So what do you mean by kind of unaccented?
That's a fantastic question, because saying unaccented is very ethnocentric. And that's why I try to specify unaccented, sort of Midwestern American speech. Right now, we're only in the data set that I was describing, we're differentiating between flat American speech and English spoken with any other accent. That would include, for example, British accented speech. And in the data set that we're currently collecting a much larger data set. We're trying to collect, rather than having people label the data, we're collecting the ground truth of what would you say your native language is, with a bunch of different choices for English, British English, American English, Australian English, and a lot of other language choices to try to go beyond accented and unaccented, which really means this group that we had a lot of and everybody else.
Right.
Yeah. No, that's a fantastic question, not a strange one.
So it's kind of following along that, I guess, first of all, would there be a use for a machine that could kind of interpret literally anyone? And then in the making of that, would it be more equitable, more kind of successful at understanding everyone if we just threw all the data at it, if we could literally get everybody on Earth?
Well, that hasn't worked so far. Literally throw as much data at it as we can get results in something that works well for majority classes, and doesn't necessarily work well for everybody, because that's what machine learning systems do, right? They find patterns that are common, and they learn to focus on those patterns. So in a perfect world, what we'd want is a system that perfectly understands everybody, right? That's the holy grail of speech understanding. But in practice, just adding progressively more data doesn't mean that we perform perfectly for all of the groups that appear in that data.
Even if you were to say, continue adding more data from the groups that you weren't doing as well as. In other words, could this be solved by infinite data?
I'm a machine learning person. I'll tell you anything can be solved by infinite data. But in practice, we're always working with even the bodies, even Meta or Google, who have access to data sets that are on the order of billions, have these extremely inequitable slanted systems that come out. Because it's very difficult to build a system that works perfectly for everything. If you had infinite data, then you wouldn't have any new data in the training set, or in the testing set. But short of that, there aren't machine learning systems that perform perfectly, even given this very, very large scale data.
Gotcha, thank you.
Currently.
These are two simpler questions, I guess. One, I was curious, what was the robot that you guys used for this?
So we're using a robot that we sort of built in-house. It's a Husky base, if that means anything to you. It's a little robot on 4 wheels that's about yay tall, that's meant to move around with a custom platform built up on it and two arms that are mounted to the top of the platform, what's called JACO arms.
Okay, so,
So-
not a COTS one.
No.
And the next one, with your robotic environment, is that something, like, I don't know, is there a repository for robotic environments already? Or is that something that,
There are a number of different people working on sort of virtual environments. The simulator that I'm describing has a repository, and we've got the environments that we're working with in that repository.
is that open source? Or?
It's not far enough along to be just widely open, but if you get in touch with me, I'd be happy to work with you on installing it and giving us feedback on it.
That'd be great, thank you.
Yeah, we want people to use the simulator. That's its purpose.
So I really like that each individual can be customized to respond by just interpreting their speech versus just having, this translated form of text. Does that mean that each new person or application that this encounters kind of has to go through this like retraining process with their speech, or is there a starting point that you can kind of go from?
There's a starting point, and I've been giving sort of simple examples, but there's no reason every robot should need to learn what an onion or an apple or a color is. We would start with, an existing model and then build onto that and learn to understand better how people are referring to things that the robot already knows about and so on.
Okay, and then so each person that may have variations in their speech, it would kind of be trained a little bit at least to
Right, it would
to handle
build on,
those.
yeah.
Okay, thanks.
Hi, my question is about the people who are interacting with your machines. Do you find, or are you measuring for the way people change their approach in interacting with your machines, and if that improves the interaction?
That's a great question. It's not something we're currently measuring. There's been a lot of research on how humans adjust their behavior if they're interacting with robots versus other people. But from the perspective of the work I'm doing, I'm interested in how they interact with the robot so that they can subsequently interact with the robot. So it's going to be a consistent performance from, throughout the learning process and the actual application process. What people have found is that people do interact differently with robots than they do with other people, but those differences tend to wear off. People start adjusting how they interact with the robot to be consistent with their perception of what the robot's capabilities are.
Does their word choice change over time, or the way they structure their sentences change the more they interact with the robot?
We don't have enough longitudinal data to answer that question right now, and it's a good question. We don't have a lot of interactions of people who, we have data sets of people who provide this training data, and then we have these relatively short, less than an hour testing interactions. We don't have data of people, this is lab technology at this point. We don't have data of it being deployed in a bunch of people's homes to see how it changes over time. And that kind of longitudinal data is something that I look forward to getting to the point where we are able to collect it.
Thank you.
Sure. Other questions? All right, thank you again very much for the opportunity to talk to you. I've really appreciated it.